So in this video, we'll talk about fundamental counting principle, permutation, and combination. They are actually related, and we're going to start with fundamental counting principle. And I'm going to give you an example. Fundamental counting principle states, if you can do task A in M ways and task B in N ways, then you can do task A followed by task B in M times N ways. Now, it doesn't make a whole lot of sense, but let me give you an example. Let's say Jeremy has 3 shirts and 2 pairs of pants. How many different outfits can he wear? Let me take this to a different page, okay? Give me 1 second. Okay. So remember, we said Jeremy has 3 shirts and 2 pairs of pants. So these are his 2 tasks. He's going to choose a shirt. He's going to choose a pair of pants. How many ways can this be done? Well, it's according to fundamental counting principle, it's this 3. How many ways he can choose a shirt? 3 times how many ways he can choose a pair of pants? 3 times 2, 6. Done. Right? That's fairly straightforward. And this is fundamental counting principle. And you can see it in a variety of contexts. I'm going to give you one more example. For instance, suppose you have a pizza that the pizza, you have 2 choices for the crust, thin or deep dish. And for the topping, you have 3 choices. How many different pizzas you can get? They're going to put the sauce, they're going to put the cheese. You have no control over that. You can choose crust in 2 ways. You can choose a topping in 3 ways. So the answer will be 2 times 3, 6. Okay. That's the basic idea. So I'm going to give you a very concrete example. Check something here. Okay. So let me see what I can do. So he has 3 shirts and 2 pairs of pants. So each shirt can be worn with one of the pants. 3 shirts can be worn in 3 times 2, 6 different ways. And if you scroll down, so the gray t-shirt can be worn, 2 outfits with gray t-shirt, 2 outfits with the pink shirt, 2 outfits with the blue shirt, 3 times 2, 6. Now I had to do it in multiple pages, okay? So that's the idea. And this is called tree diagram. So here's you can do it in short like this too. Pants 1. So this time I have 2 pairs of pants and 4 shirts. So pants 1 can have 4 outfits. 4 outfits can be created with the first pair of pants. Another 4 outfits can be created with the second pair of pants. So using fundamental counting principle, it's 2 times 4 is the total number of outfits he can have. It's a little repetitive. It works for more than 3 cases. We're talking about shirts and pants. If you have shoes, hats, you can use the same principle. So this one is you have 2 types of soups and 3 types of entrees to choose from. First, how many meals can you have? Soup 1 can be in 3 meals. Soup 2 can also be in 3 different meals. So the answer is 3 times 2, 6. I'm not going to go over this, but it's worth actually going over. So now, this doesn't look like a similar paragraph, but it is. So let's say I want to rearrange the letters in the name Fred. The first letter can be picked in 4 different ways. You can choose F or R or E or D. Now, the second letter, one of the letters is gone. So I'm going to show you here. Actually, I'm going to do some So the first letter can be picked in by four choices for the first letter. Four. For the second letter, one of the letters is unavailable. I don't know which one, but I know one of them is gone. So I can choose the second letter in three different ways. I can choose the third letter in two different ways. I can choose the fourth letter in one way. So the answer is, using the fundamental counting principle, is 24. Now, if you look at this page, here I tried to list all the different outcomes. You have F, let's say you chose F for your first letter. Then the second letter could be either R or E or D. If your second letter is R, your next choices could be either E or D. And the fourth choice is fixed, either D for this one. Let me see. So this is your first choice. And if you choose F, R, D, and E, if you choose F, E, R, D, F, E, D, R. So if you have to list all the, let me get rid of this mark, guys. Okay. So if you have to list all the possible outcomes, you have to use a tree diagram. If you just want to know how many ways it can be done, you can use the fundamental counting principle. All right. So how many different ways can you arrange five people in a row? So the first position, so let's take it. I know it's here and everything, but let's try to do it in try to do it a little more carefully. Okay. Right. So you're going to arrange five people in a row. How many ways can you do it? Well, you have five, okay? You have five people in a row. You want to arrange five people in a row. Let's say you have five spots, okay? These are, pretend they are five chairs, right? So I have five chairs, okay? How many ways can I choose a person for the first chair? I have five choices, right? So I have five choices. How many ways can I choose a person for the second chair? Well, four. One of the people is gone. Three, two, one. And you multiply them. Why? Because because that's what we mean by fundamental counting principle. Now I don't like it. It looks like I have 5x, 4x. Let me get rid of it. So let's see what's going on here. So the answer is gonna be 5 times 4 times 3 times 2 times 1. By the way, that's going to be 20, 120. Okay. So one more thing, guys. We don't write 5 times, 4 times, 3 times, 2 times 1. It gets very tedious very fast. What we really do is we call it 5 factorial. If you write 5, then an exclamation mark. It's read 5 factorial, and 5 factorial simply means 5 times, 4 times, 3 times, 2 times 1. 50 factorial. 50 factorial would mean 50 times 49 times 48 times 47, all the way down to 1. Okay? 1 factorial is 1. And this is going to throw you guys off a little bit, but might as well mention it. 0 factorial is not 0, it's 1. Okay? Think about arranging 0 people in a row. How many ways can you do it? One way. There's only one way you can arrange 0 people in a row. Nobody sits. The chair is empty. Okay, that's one way to handle it. It's a difficult idea. Just accept it for now. But here I gave you an example. Okay, 0 factorial is 1 because how many ways can you arrange 0 people in a row? The answer is 1. The answer is not 0. All right, so we're going to move on. We learned how we use factorial. We also learned why 0 factorial is 0 and 1 factorial is 1 is also, excuse me, is pretty straightforward. Okay, 1 factorial is 1 because how many ways can you use one person in a row? 1. Let's say how many ways can you have Jack sit on a chair? 1 way. If Jack is going to sit, he's going to sit there and that's it. So keep these two in your head, okay? Make sure you understand them as well. See what else is coming up. So it's a little repetitive, right? Okay, here's a good problem. Okay, here is a good problem. We're actually making good progress. Now, so far, we have had 5 people, 5 chairs, 6 people, 6 chairs, and that's easy. Now we are saying how many ways can you choose 5 people in a row of 3 chairs? Okay, 5 people. This the word of is missing. Let's put it here in a row of 3 chairs. Okay, so these are my 3 chairs. These are my 3 chairs. How many ways can I choose a person for the first chair? 5. There are 5 people. I'll grab one of them. Then I have 4 people to choose from. I can only put a person on the second chair in 4 different ways, and then 3. So you can say the answer is going to be this. Okay, the answer is going to be 5 times 4 times 3. This is simply fundamental counting principle. Okay, this is also, well, let me tell you one more thing here. Okay, so um, this is 5 times 4 is 20, 20 times 3 is 60. Done. Okay. Now you can say this is 5 factorial, but you can do this. You can do this. You can say we like the factorial notation, right? Because it's very compact. You can easily do this. So be a little patient. Now, I really multiplied because I want to write 5 factorial somehow. I want to use the factorial notation because it saves time. Uh, on top, I multiplied 5 times 4 times 3 by 2 times 1, kind of complete the factorial notation. So I have to divide it by 2 times 1. What do I have on the top? The top has 5 factorial, and the bottom has 2 factorial. You can write it like that, okay? So this has another way of writing it. Let me see if I can nicely do it. So let's see. Do I have a choice here? Boy. Okay. So, so this is called permutation. Uh, Permutation is about arrangement and when order matters. So when you're arranging 5 people in a row of 3, you are arranging and the order matters. So you have 5 people, comma, how many chairs? 3. So this is read 5 permutation 3, and I don't have a way to officially type it, but you can write it like this. That's acceptable. People also write it like this. 5 permutation 3. So the context for 5 permutation 3 simply means 5 people, Three chairs, how many arrangements? Of course, the people are different, so how you arrange them, the order matters. Okay, so 5 permutation 3 is simply equal to, I am not gonna write this notation, this one, this is complicated. I mean, we can use it when you're using your paper pencil method, but it's hard to type. So 5 permutation 3 is simply 5 factorial divided by 5 minus 3 factorial. And 5 minus 3 is what? 2. That's exactly what we got here. So let's do one more here. Okay, let's do one more. Let me type the question. How many ways can 7 books be arranged in a row? We probably should say 7 different books. That's kind of implied. Nobody carries 7 identical copies. How many ways can 7 different books be arranged in a row? Again, order matters. In a um, row. That's pretty straightforward, right? That's going to be 7 factorial. So the first position can be filled in 7 ways, then 6. So the answer is pretty simple, 7 factorial. Now, let's make it a bit more challenging. How many ways can 7 different books be arranged in a row that contains only 3 books at a time? Row that can only hold exactly 3 books. Well, what I'm trying to say basically is like 7 people, 3 chairs. Okay, 7 people, 3 chairs, or 7 books, 3 spots, right? So how do we do that? Well, we're talking about arrangements and it's a permutation problem. You can simply say it has to be 7 comma 3. And 7 comma 3 is 7 factorial divided by 7 minus 3 factorial. And that's going to be 7 factorial divided by 4 factorial. You can leave it like that. Most texts or most exams will give you full credit. There's nothing wrong. You can use the calculator to find that. Let me see if I can show you how to use the calculator. I don't think this one has factorial notation, but I'm going to try it, okay? 3 factorial. Oh, good. It does have it. Okay, fine. So 7 factorial over 4. 7 exclamation mark over 4 exclamation mark. And that's 210. Fine. Okay. Most calculators will have a factorial key. Depending on what kind of calculator you have, you'll have it. Let me see. But you can use your factorial key. This is Desmos. So that's fine. That's 210 from my calculator, but I can do it from scratch too. So I have 3 spots, remember? Going back to the spots, I have 3 spots, and you can use the fundamental counting principle. Okay. Now, the first spot can be filled in 7 different ways. The second spot can be filled in 6 different ways. The third spot can be filled in 5 different ways. And 7 times 6 times 5 hopefully is 210. And we're going to find out 7 times 6 times 5 is 210, as you can see. So it works either way. It works. So this is about permutation. Once again, permutation is about uh, permutation is about arrangements. Arrangements always mean order matters. Okay? And in combination, the order does not matter, and we're going to get to it. Let me see. Well, we're going to do another video. So today we learned that permutation is basically a special case of counting principle. It's basically counting principle with some conditions, right? You can't choose the same thing twice because you're arranging. If you're arranging people, the same person cannot take two spots, all those things. So permutation is a special case of basic counting principle. Next video will be about combination, which builds on permutation. All right.